Hello, Michelle. Hello, Chris. Hello, Maria. Hello, Cheska.
Hi, Professor.
Hello. Thank you for he even waves now. There should be a portal for waving. Okay. Hello, Yavi. Oh, there we go. Okay. Good afternoon, Katie. Good afternoon, Shy. Afternoon, Shy. Yeah. Good afternoon, Michelle F. Good afternoon, Brooke. Good afternoon, Mohammed. Good afternoon, Emily. Good afternoon, Marilyn. Good afternoon, Maria. Good afternoon, Jessica. Or afternoon, Maria. Good afternoon, Sue Chef. Good afternoon, Allison. Good afternoon, Yavi. Wait, I know there's more people in the waiting room. Why? How do I do the waiting? Okay. Good afternoon, Fariel. Good afternoon, Victoria. All right. All right. We're going to get down to business. First of all, I have not yet put in Google Classroom, but you may have heard a rumor and it is true. Well, depending on what. So I am, I hope, so I'm postponing the exam by 1 week. I'm rescheduling. Like it's supposed to be posted tomorrow. I'll put this in Zoom. I mean, I'll put this in Google Classroom. Good afternoon, Michelle Q. Sorry. I will update Google Classroom. The exam was supposed to be. I'll put in the chat right now to just so it's in print. Hold on a second. What I'm saying is the exam is supposed to be posted tomorrow night and supposed to be due back Monday. But for good or for bad, and we're going to give you another week. If that conflicts with something else that causes you a huge personal problem, let me know personally. But hopefully that's good I think that hopefully that's better for most people. So let me just put in the chat now to be clear. I'm saying, so it's 1 week extension or postponement.
Quick question.
Yes.
Can I possibly negotiate about the due date? Because I know a bunch of us are in quant in here, and our quant midterm is going to be dropped on the 31st.
Wait, wait. And good afternoon, direct chat person. Wait, the 31st. Wait, I thought we had sort of wait. So you mean you wanted to stay? I mean,
Can I negotiate that it be like instead of due like that Monday right before class, it'd be due that Thursday right before class or Wednesday right before class? Can I negotiate that?
Okay. I appreciate your okay, so you're saying I mean, so yes, the answer is you can go. So I mean the answer is yes, I'm hearing that. Wait, so
Just so that way we don't have to do 2 midterms in the same weekend.
Yeah, no, I definitely don't want you to do 2 midterms in the same weekend, right? And for some reason, I thought I'd already figured this out, and I thought most people didn't have this conflict. But okay, I won't take a huge amount of class time today. But I'm okay. Let me just look at the calendar. So you're saying,
I'm like, the only reason why I'm asking is because I know it affects more than at least 3 of us.
right? No, that's important. That's hold on, I'm looking. Okay, so you're okay. I think one thing I can do. Wait. Yes, I'm just looking. I'm looking at the chat now too. You've quantitative. Yeah. Okay. Um. 1 second. 1 second. The door is locked. Hold on. I'm looking at the chat and I'm hearing this. Okay. So what if it's so your quant thing is getting posted on Sunday, but you're getting 4 to 5 days. Oh, so that almost makes this worse. I mean for everybody. So you're spending. Oh wait, which Sunday is your quant thing getting posted?
31st.
Okay. Wait, so it's at the problem, I'm totally hearing this. Wait, someone's in the waiting room also. And I don't want to spend all of class figuring this out. Like I will, all right, so I'm taking this into account. But if I'm understanding correctly, like what I was about to say, I mean, I can do this, what I can easily do, but it sounds like it will still make it worse. What I could easily do is say that your physics midterm wouldn't be due the Monday that I was about to say. I could certainly easily say make it due the Wednesday. I know you're saying Thursday, but I could make it due the Wednesday without like any issue. And I could think about the Thursday part, like, I get back to you. But I just want to make sure I understand one thing though. Doesn't that make it, that means you're spending that whole week on both of these? Like, it sounds like then that literally lands at the same time as your quant. Is that not? Yeah. She says, yeah. Okay. All right. Let me put it this way. I'm totally hearing this. And I actually do care about your input. Like, and I do not want to conflict with another class that directly. For good or for bad, what I'm not going to do is go back. Like, it sounds like it might even make it better for you guys if I just kept the midterm the way it is, but I don't think I can do that. Like, I mean, I hope, I don't know if that's what you're at. Well, I'm not sure if I even want to ask if that's what you're asking, but,
I mean, I was asking because I didn't want to push the boundaries of your kindness. I was just asking for it to be due that following class that Wednesday instead of that Monday.
but that I could wait, I can definitely do that. I mean, that is, no, and I appreciate it.
I
Yeah.
didn't assume you were going to do anything else besides that. I'll be
Okay, yeah,
honest.
all right, so for the moment, so I'm not going to write this down yet, everybody. No, that I can easily do, and I definitely do appreciate hearing this. I mean, the thing I'm nervous, what I don't want to do is keep it the way it is. Like, even though that it sounds like maybe that might even be better for some people to have it earlier out of the way before quant. That okay, I'm looking at the chat. Okay, so I can't. So all right, I'm informally saying right now, if making it that Wednesday helps at all, that's no problem. All right, I'm gonna write in the chat tentatively, okay? But I'll still think about what you're saying if I could do better or whatever. But I'm gonna type tentatively in the and because I know not everybody. Okay, so let me just okay. Okay. So what I just wrote in the chat, just to make, we're gonna move on in a second. I'm saying tentatively because I'll still, like, you guys can email me later or whatever. I know this is still not ideal because of quant or with quant, but is what I just posted, is that somewhat of an improvement based on is that somewhat of a hearing of what Katie is saying? I guess I'm asking Katie, but I'm asking everybody. I mean, it still doesn't sound ideal, I know, but I mean, of course, at a certain point, it's life and all of that. But is that's better? Okay, that's what I'm looking for. Okay, so all right. Thank you. I appreciate all the feedback. So I'll still think about it and stuff. I'm hoping that also means it's better than what it was now, but maybe. Oh, thank you. That's very nice. Thank you. It's okay, and I definitely understand it's not ideal if we don't do any, but I will eventually fix it in Google Classroom. Okay. Well, I'm all right. Thank you. I just. Okay. All right. Cool. Thank you, guys. I cooked. Okay. All right. Thank you. No, thank. Okay. Oh. Oh, yes. Okay. Interesting. All right. Well, this gives us time. I'm seeing other things in the chat now. Now, here's the thing. Part of why I'm doing this, I mean, part of it is for totally things on my side. This gives us a little bit more time to like nail down the midterm. Like, so for example, yes, there's that video posted that you see now where I walk through. I don't want to get too involved in this right now. So the practice midterm has 4 big problems, right? And even in and you eventually get some kind of choice. You don't do all 4 of the problems, but you're responsible for knowing how to do all the 4 problems, right? And as someone's pointing out in the chat right now, there's a video that I posted where I walk through in great detail 3 of the problems. And some people are saying in the chat that they still have some questions about that or some confusions about some of the walkthrough. That's totally fine. And I would like to address those questions. That's part of the point. This gives us a little bit more time to do that. I don't think I'm going to get deep into addressing specifics of the practice midterm or the video today. But now we do have a little more time for me to do that. Like Monday, you can remind me, I mean, honestly. But noted that there's in the chat some questions about like question 3 and stuff, which I'm sure is the pendulum question. And yeah, because that's like probably question 3 is probably like the newest looking or hardest application of everything we've done. I mean, it's putting together lecture math with lab concepts. So yeah, I certainly could say more, whatever. I could certainly say more about question 3. But also just to note, I don't walk through question 4 in the walkthrough video, but to note, question 4, problem 4, which is the most sort of free form of the problems, that's what yesterday's lecture was, or Monday's lecture was. Now, I'm like literally, like you're supposed to show me in your words, in your math, in your diagrams that you understand your way what I presented 2 days ago, which for good or for bad, I had to post it. I mean, hopefully you were there and you took notes and all that. But the question 4 is the video and notes from 2 days ago. Okay. Okay. Oh yeah. Okay. I'm still in the chat right now. Okay, give me a second because there is something in the chat. It's all legit. Hold on. I guess we're doing some. Hold on. A lot of things are happening. I'm losing. Wait, sorry. Wait, sorry. So something else in the chat. Okay. Something else in the chat. Someone pointed out very helpfully that I had not yet posted a game thing for tonight. So thank you. So I just did that. So that you should see that now. But then, yes, the comment on the video, I posted the video and then you posted the comments and Google Classroom saying you're late about that because of the original deadline. But no, that's totally on me. You won't be marked late. You'll get the full points for them. I'll try to remember to change the thing on Google Classroom so it doesn't say that. But no, you absolutely, you weren't late. I was late with the video. You will get the full point. Okay, thank you, and thank you for circling back. Okay, so that's all that stuff from the chat. So you can remind me on Monday. You can ask me questions about the videos and stuff, but basically, right, there's in effect, it comes down to one full long video to help you with questions 1 through 3, and then yesterday's or Monday's video material and notes to help you with question 4. And yes, Mondays, unfortunately, it wasn't our direct recording because that failed, because I failed, but it is that material. Okay. And hopefully so what I want to do today, if that covers, so I want to keep going through with the material, proceeding with the material in ways that are relevant to upcoming homeworks and labs and stuff like that. So I'm just going to keep going now. If that's okay, with like lecture material. Let me change the view of the screen. Okay. where we got, yes, so, well, in summary of the last few days, we decided. So this is lecture material now that I'm doing, and it's about everything. It's relevant to everything, and it's ultimately, I suppose, directly feeding homework 4, which you'll do after the midterm, or which is not part of the midterm. But it's like just lecture material. It's not. I'm not answering a direct question. I'm just talking. And right now I'm summarizing that what we established from lab 3 and lab 4 is that up on the board, right? And what that really means, this is real. Okay, this is really, if anything, that conclusion. What this says on the board is that if you take a whole bunch of identical vertical oscillators, distribute them along a horizontal axis, distribute them uniformly. So you place identical vertical oscillators at equal spaces along a horizontal axis, and then you stagger their phase by a constant amount, right? Make it so that each one is out of phase with its neighbor by the same amount as its neighbor is out of phase with the prior one. If you do that, the entire collection can be described by this equation. And then what you'll see, if all of these oscillators are going up and down in an identical fashion, but all in staggered phases, what you'll see is a wave propagating along the x-axis through the medium of this collection, right? And what we did was we took two partial derivatives of each kind of this equation. Well, yeah, to cut to the chase. Okay, I'll do. So we took two partial derivatives with respect to time of this equation, and we got oh, sorry, no, we didn't. I mean, we did, but and then we related those derivatives to each other, and we found and we found this, right? We said that the relationship between the two partial second derivatives, that the relationship was this, and we said this. So we have a collection of phase staggered oscillators. We have a bunch of particles that each of which is oscillating cosinusoidally in time, and we've arranged them so that they are oscillating cosinusoidally in space, right? That's what we're saying. We've arranged them so that their phases are staggered, in effect, cosinusoidally. And when we take 4 derivatives of this description, we get this second order partial differential equation. Mathematically, physically, what we get is wave motion. So we say from now on, this thing at the bottom of the page, this is the wave equation. Specifically, it is known as the one-dimensional wave equation. One-dimensional, well, so I'm going to write that on the next page. So we're saying from now on, now this is known as the 1D wave equation, specifically because the medium through which the wave is propagating, the medium is one-dimensional. Right? Like this all came from in lab 3. It's crests and troughs flowing along a line of metal, right? As opposed to wave pulses propagating on the surface of a pond or the ocean or something. Those waves are also waves, but those are waves propagating through a two-dimensional medium, a surface, like a surface of water. They all follow the same math. It's all the same math ultimately, but this is like one axis of what's happening with them. So this is the one-dimensional wave equation. This is what so anything that obeys this is a wave, and anything that is a wave obeys this. So the question is, what does it mean to obey this? Like, what is this thing actually saying, right? Now so we're going to look at what this equation is saying physically. This equation is a second order partial differential equation. We have had one other second order differential equation in this class. Like this is our second differential equation. Let's compare this one to the other one that we know and the one from which this one was kind of derived. So the original equation that we have spent a lot of time on in this class is the mathematical version of Hooke's law describing one individual oscillator, right? The original differential equation we have is this. Oops. Right? So imagine you have one of those oscillators that's going up and down the y-axis in time. Then we know it's described this way, right? And this came from that differential equation originally was just applying Newton's law to Hooke's law, right? That original differential equation is all about a restoring force. What does it mean in English? Oh, what just happened? 1 second, sorry. Okay, the left. Okay, the left side is acceleration, right? I mean, the left side is second derivative of position with respect to time. So it's derivative of position with, it's derivative of position with respect to time. So it's derivative of velocity. So it's acceleration, right? That's what the left side is. But specifically, it's acceleration along the y-axis. It's all acceleration along the one and only axis that the oscillator exists on, right? It's so it's the so if the oscillator is a mass on a spring hanging down, it's the rate at which the mass accelerates along the y-axis. Accelerates where? Accelerates to back to its equilibrium position, right? And the right side is the right side is saying, first of all, there's a constant in the parentheses, right? Omega squared is definitely a positive constant. Happens to be angular frequency and all that, but I don't even care for the moment that that's what it is. I just know that it's a constant. So far, if I'm reading this differential equation, I'm saying some kind of acceleration is equal to a constant times something. So that means so far what I'm reading is that acceleration is directly proportional to something, right? If you're equal to a constant times a thing, that means you're directly proportional to a thing. And the thing here is the variable y, which means in this case, y is measuring displacement from y equals 0. And what's y equals 0? The equilibrium position, right? So just to remind you, like right now, I'm not saying anything new. I'm just trying to, I mean, hopefully this is maybe a little bit helpful for the midterm or whatever, but right now, I'm like reminding you or reviewing something, but I'm doing it on purpose to set up a compare and contrast kind of deal. So I'm saying, let's remember that each individual oscillator, it's being governed by this differential equation. This differential equation really is Hooke's law. It's really saying F equals negative X. It's really saying F equals negative KX, but then applying that to F equals MA. So it's A equals negative KM over X, negative K over M times X. So what it means in English, once it's written this way, is it's saying if you are a little mass on a spring, and wherever you are, you accelerate back home to your equilibrium spot at a rate that is directly proportional to how far you are from home, right? That's what, again, that's not new, but I just want that to be in focus in your mind. Like in the extreme case, if the oscillator is already at home, if it's at equilibrium at y equals 0, then it has no acceleration at all. It might have motion, but it has no acceleration. It's right. But as it gets farther and farther away from equilibrium, it accelerates back toward equilibrium at greater and greater rates, right? You knew this. This is not new, but this is what this is saying, right? And in effect, what this differential equation is saying is just putting mathematically the whole concept of a restoring force, that you are in this case, a restoring acceleration, that you get restored back to equilibrium at a rate that is directly proportional to how far away you are from equilibrium, how far stretched away you are. Okay, so that's oscillation. But now let's look at our equation that we just established and compare. Okay. On this side, same thing, not a coincidence. On the left side of our wave equation is the same concept. Now it's a slightly different symbol. This is now a partial differential equation, right? It's those backward sixes, but that's only because we're acknowledging that we now have a function of two variables, x and t, whereas over here, I should have written somewhere, here we just have a function of one variable, t. Right, so the kind of derivative that we're taking here is a partial derivative. We're just taking derivative with respect to time and acknowledging that there's another variable as well, another independent variable as well that we're holding fixed. So it's a different symbol, but what we're doing here on the left side is exactly the same. We are looking at the rate of acceleration of a particle or of something along the y-axis. So here on the left side, if this whole equation is now describing like a wave, right? If this is one snapshot of your string wiggling back and forth, and this wave equation is supposedly capturing it, then we're looking at some point on the slinky. And the left side is referring to the rate at which that point is accelerating somewhere, right? But certainly the rate at which it's accelerating along the y-axis. I don't know why I just drew it like that. Like that. Okay. So the left side is still, so picture in your mind, picture like the other example, the other equation was a oscillator. Now you're picturing a wave or a slinky through which wave pulses are propagating. So now I'm asking you, picture some random point somewhere on the slinky. The left side of this equation is referring to the rate at which that point is accelerating along the vertical oscillating axis. That's the left side. Now the right side, well, here we have a constant again. It's not the same constant as before, but it's still a constant. I mean, it's a constant divided by a constant squared. That is still a constant. Also, you might just sidebar note, it's very related to the constant in the other equation. I mean, the other equation is somehow angular frequency in time squared. And this one seemed to be angular frequency in time squared divided by angular frequency in space squared. I mean, that's what that really means. So it's in a way, it's very not surprising and very fitting that when we went from the harmonic oscillation to the wave, we're just like adding the space element to things. But now we get to the rest. We get to this part. Now, this is a little bit more complicated. Like, so far, what this equation is saying is much like the other one. This is saying acceleration along the y-axis of some piece of the medium through which this wave propagates. The acceleration of the y-axis, the acceleration of that piece along the y-axis is directly proportional to something, right? Equal to a constant times something. The question is, what is the something? In the other equation, the something was displacement from equilibrium. The farther away you are, the harder you accelerate back home. The farther away you are from home, the faster you accelerate toward home in the other equation. Here, this piece does not just say displacement. It doesn't just say y. It says some kind of second derivative of y. Okay, that's a lot. The first thing you might say is, wait a second, I thought the second derivative was already on the left side. Like, are we going in circles here? Like, I thought we already talked about a second derivative on the left side. We did. We talked about a second derivative with respect to time. Now we're talking about a different second derivative. Now we're talking about a second derivative with respect to space. So this is not acceleration anymore. The left side is acceleration. Acceleration is directly proportional to something. The something is what's written on the right side. The question is, what is that something? Now, I'm going to ask you, I'm going to pause for a second so to give you a hint to catch us up. I'm saying okay, so I'm going to ask you, and I'm going to ask you to put the answer to this question in the direct chat. And I'm going to wait till I get like, at least 3 people or something in the direct chat, please. If you were in a math class, before you did all this, if you were in a calculus class, like Calc 1, before you did all this physics and stuff, they introduced derivatives with graphs, y equals function of x, things like that. Like they don't care so much about time in a math class, at least not at first. They're just giving you regular generalized mathematical functions, x and y. Right now, when we think about x and y in physics, we think about space and space, right? Like this graph right here has nothing to do with time, right? It's just a picture of how high a piece of string is in relation to how far over you're looking at the string, right? So this graph right here is pure y and x. It's like a math class. When you first learned about derivatives in a math class, when you're thinking about their meaning graphically, on a graph, the first derivative of y with respect to x is regarded as slope, right? The way you picture what you're measuring when you measure first derivative on a graph, such as y of x, right? When you picture taking the derivative, what you picture is measuring the slope of the graph at a point, right? That's a statement. That's not a question. In other words, first derivative is graphically slope in a calc class. In a calc class, when you're just doing y-x graphs, if first derivative is slope, what is second derivative in a math class? That's the question I'm asking for in the direct chat. I'm going to ask it again. I might even write it in the chat. My question is, in calculus, if first derivative measures the slope of a graph, what does second derivative measure of a graph? I'll write it in the chat. Okay, I see. So I'm not going to comment right or wrong yet, but I see things happening in the chat. That's awesome. Okay, hold on. I'm going to write. I see things happening in the chat. I'm still going to write my question in the chat because I want to get a lot of people, and also I want to make it as super clear as possible. Okay, I'm seeing a lot in the chat. This is cool. I'm going to comment on these chat things. I mean, out loud, I'm going to comment. Hold on. Okay, cool, cool. Here's the thing. Cool. So I see a bunch of answers. None of them yet is exactly I'm looking for one word, by the way. There's one word that you know for this. And a lot of people have sort of described it. So let me read some of these. This is good. You're obviously understanding the question, which is good. And when you hear the answer, you're definitely gonna be like, oh, yeah. Like you definitely know this word, but you're describing it well. So what people, someone just got it. All right. I'm still gonna keep going. One person just got it. That's awesome. But that's, hold on one second. I'm just gonna compliment that person. Okay. I'm going to read a couple out because they do describe the thing very well, what I'm saying. Like first derivative is slope. So for example, one person's saying then second derivative would be the rate of change of the slope. And that is true. Like if slope is rate of change of the graph, if slope is the rate at which the graph is changing, then what I want is the rate at which that's changing. I want the rate at which slopes are changing. That is true. In other words, I want to know, like, so slope can even refer to a straight line, right? Like you can have a constant slope of a straight line, but the higher the slope, the steeper the line. Once the slopes are changing, the line starts curving, right? So if you were to measure the rate of change if you were to measure the rate at which steepness was changing, you'd in a way be measuring like some kind of curvature of the graph. And there's a word for that at least one. So there's a word for rate of change of slope that you know from math, and at least one person's written down. So so here's my hint again. I'm looking for the word from math class that basically means the rate at which steepness is changing, or in other words, the rate at which the graph is curving is what we're looking for here. And it's like a physical word like that. It describes something about the shape of the graph, the rate at which, yeah, we're looking at like the rate at which the slope is changing in respect to time. But also I want to warn you guys, something that what's confusing here, and the reason I'm stopping on this and dwelling on it is those of you who are using words like velocity or acceleration, I just want to remind you, velocity and acceleration come into play if it's a y of t graph or an x of t graph. When time is involved, that's where the calculus from your math class like meets the physics. When time is involved, then the rate of change of position with respect to time is known as velocity. And the rate of change of that is known as acceleration. That's when time is your independent variable. And that's what's going on the left side of this differential equation. But now I'm looking at the right side. The right side doesn't have to do with time at all. It's literally looking at vertical space as a function of horizontal space. So I'm looking for a word here that doesn't have to actually do with velocity or acceleration, a word that has to do with shapes in space, of pure graphs or of pieces of string in space. So, and again, one person has nailed it, but so we're talking about, another person just nailed it. We're talking about how the rate at which the steepness changed. The steepness is slope. So steepness is first derivative. We want the word for when the steepness isn't just a thing, but is a changing thing. And someone just say, hold on one second. And I'm going to stop talking in a second. I mean, I'm going to say, but. Okay. Now, a number of people have okay, so I'm going to stop. I'm just going to respond to them and congratulate them, and I'm going to stop. Okay, so yes, the word that, and again, so the word I'm looking for, the word that I think you guys do know, or the word is concavity, right? Right, and does this okay? And is this familiar? Like, and maybe what I'm saying is, if you're just looking at shapes now, see, this is what's sort of tricky about this. First, you learn about these shapes on a graph in a math class, y equals f of x. Then you have to start making the extension in physics that, sorry. You learn these graphs in math. Then you have to learn, or it gets sort of emphasized that they're just graphs. They're just representations of numbers. They don't necessarily, what just happened? Okay. They don't necessarily refer to any shape in space. They're just a shape that represents a bunch of numbers. Then you get to physics and you start seeing that the x-axis of these graphs often represents a clock ticking, right? So you see a two-dimensional shape and you get used to realizing that the two-dimensional shape on a graph of axes is actually representing something moving in one dimension of space through time, right? But now I'm circling back. Now I'm saying, hold on a second. Now we're looking at something. We're looking at this long stretched string where each piece of it is doing something in time, but also the whole thing of it is stretched out in space. And And so any given snapshot of this whole stretch string itself is a graph. Any given snapshot of this whole stretched slinky is a graph, not a y-t graph, but a y of x graph, just like the old days in math. And in a y-x graph, first derivative measures how steep the graph is. Like the bigger the number, the more higher up you go for every step you take over. The bigger the number of first derivative, the more rise you do for every little bit of run, right? But the derivative of that, the rate of change of that, is how much the steepness is changing, i.e., how much it's curving up or down. And we call that concept concavity, right? If the graph looks like a big bowl, a really curvy bowl facing up, we call it concave up, right? And that means the second derivative is positive, and vice versa. If it's like opening down, we call it concave down, and the second derivative is negative. And if it's flat, we say there is no concavity, the second derivative is zero. So what does that have to do with this? I'm saying if we now look, so I'm saying the word is concavity. Yay, good job. And for I'm hoping and assuming from experience that many of you, even if you didn't quite know what I was asking or you didn't quite say that word, I'm assuming that many of you, now that I'm saying the word, you know what I'm talking about, I think. The second derivative, so the second derivative of y with respect to t, so the left side, the second derivative of y with respect to time is acceleration. But the second derivative of y with respect to space, with respect to x, that is concavity. So now what am I saying? I'm saying that this wave equation, what it means, if you focus on that red point, like any arbitrary, can you see? Yeah, any arbitrary little spot on your slinky, and this blue thing is supposed to be your slinky at any given moment of time, right? If you focus on a red point, what this wave equation is asserting is that at any given moment, the rate at which that red dot accelerates back toward home, back toward equilibrium, is directly proportional to how concave the string is at that point, how bent, how curved, how disturbed the medium is at that point. We're saying, here, I'm gonna write this. Okay. What I'm saying here, I think this is fabulous, honestly. I'm saying with a mass on a spring, the rate with any individual piece of this wave, with any individual oscillator, what oscillation means is restoring force. The rate at which a mass accelerates back to its equilibrium position is directly proportional to how far away it is, how displaced it is from its equilibrium position. Equilibrium is a dot, is a position, is a zero-dimensional point, and to be away from equilibrium means to be displaced along some line far away from that point, right? So it's a purely one-dimensional phenomenon. Equilibrium is a dot over here. I'm a mass somewhere over here, somewhere over here. The rate at which I accelerate back to the dot is determined by how far away along this line I am from the dot, or from the dot if it's vertical, right? But now with a wave, what we're saying is the same kind of thing happens. We're saying the rate at which the wave, the rate at which the medium restores itself, the rate at which a piece of the medium restores itself back to equilibrium is directly proportional to how unrestored it is. The catch now, the difference now is that now with a wave, equilibrium isn't a dot anymore. Equilibrium doesn't refer to a position. Equilibrium does not refer to a zero-dimensional location. Equilibrium now is a line. More specifically, equilibrium now is an orientation along that line. Like, what does it mean for your medium, your slinky in lab 3 to be at equilibrium? It doesn't mean that it needs to be at any particular place. It doesn't care how tall you are, right? Like, honestly, like the lab works for people of any height. The slinky is not trying to be here at this height or here at this height or here at this height. The slinky is trying to be horizontal. The slinky wants to be lined up along the x-axis. So equilibrium is now an orientation, a shape. To be at equilibrium means to be lined up with a full x-axis, right? So what this math is saying, what this equation is now saying is, if you take any piece of the slinky, the piece of the slinky will accelerate back toward the x-axis at a rate that's directly proportional to how bent, how concave, how disturbed the medium is in relation to a flat x-axis. It's not the farther away you are, the faster you accelerate back home. It's the more bent you are, the more misshapen you are, the faster you accelerate back to flatness, right? So this is wave motion is restorative Hooke's law motion, but hiked up by one dimension of space. Hooke's law has dots accelerating back home to other dots of space along lines. The wave equation has curves accelerating their way back to flatness, all within a plane. You see what I'm saying? Actually, I'm going to ask you, wait, just give me any kind of electronic thumbs up or any kind of affirmation if it makes sense what I'm saying. Thank you, Chris. All right, Chris speaks for the whole class. Okay, thank you, Brooke. All right, was that a, or okay? Thank you, people. Thank you. Sorry, I don't know if this is direct or if this is. Okay, thank you, guys. Okay, thank you, Maria was public, and thank you, Brooke. Sorry. Okay, awesome. That's good enough for me. Okay, so, and I think that's really cool. So, bottom line, a wave is something for which at any and every point in space and time, this equation is applying. A wave is continuous restoration back to flatness. And the restoration is directly proportional to unflatness, just like the restoration for a simple oscillator is directly proportional to displacement, right? So this is just the two-dimensional expression or expansion of simple harmonic oscillation. And again, just to remind you, I'm now saying two-dimensional a lot. Like, to be clear, this whole phenomenon is now happening in a plane, right? Like, there's up, there's down, and there's over and back. It's all happening in a plane now, whereas an oscillator was all in one line, one dimension. This whole phenomenon now requires 2 dimensions of space, at least 2 dimensions of space for it to exist. But remember, but it's called the one-dimensional wave equation because the medium through which all these propagations are occurring, the medium is one-dimensional. Okay, so the bottom line wave equation says for any and every point on the medium, the rate at which it accelerates back to equilibrium is directly proportional to how bent, distorted the medium is at that point. All the bends are continually unbending themselves, but the bigger bends unbend themselves faster than the smaller bends. That's what a wave is. And of course, every time a bend unbends itself and pushes itself down, then the string has somewhere, it needs to go somewhere, right? I mean, so the string like shoves over here, and then this part bends, and then it falls down, and then this part bends and it falls down, etc. So that's the wave equation. Now there's still, unfortunately, well, not for, there's still one more thing we have to do with that. Um, okay, so bottom line, the wave equation says acceleration is directly proportional to concavity. Directly proportional means is equal to times a constant. So now what I want to do is unpack the meaning of that constant. I'm going to do it on the next page, actually. So tell me if you need me to go back, but I mean, that's just a restatement of the wave equation. I want to unpack, I want to talk about the meaning of that constant, omega over k squared now. Okay. This is now partly to remind you and partly to say something to give you a symbol that we haven't had that in this class. So remember again, the whole thing, we're now talking about waves, right? Waves are built up from harmonic oscillations. The whole thing of a wave that's making all the math more exotic, the whole thing about a wave is that it's a function of two variables, right? The key, the underlying new concept here is that we have an output determined by two independent inputs. And again, that is new in science and in math for most of you. Like, I mean, it's not a bad thing, but we can't pretend that it's trivial. So I'm saying, like, a wave is a function of a wave means vertical position is a function of both horizontal position and time. That's why you've had to spend at least 2 labs on it. It's why in lab 3, for example, you can't ever just extract one graph that contains all the information, right? We have to have at least 2 graphs because we've got 2 independent variables independently driving a certain output, right? So that's why and that's why we take partial derivatives and all that. Like, things keep happening. And why every discussion we have of a wave, like, you always have to be careful in a wave. At any given moment when you're picturing a wave or talking about it, you're either picturing a certain X position and then talking about what's happening in time, or you're picking a certain instant of time and looking at what's happening in space. But you always have to know which one you're dealing with. And the fascinating thing is that both of the relationships are the same. So I've done that thing again right here that you did in lab 3. I'm dividing up the wave, or my attention on the wave, into 2 different relationships, reminding you that y as a function of t is a cosine graph and y as a function of x is a cosine graph. But now some terminology. If you're talking about time, like the top graph, the amount of time from one crest to the next, or one trough to the next, or whatever, the amount of time for one cycle is called period, capital T, right? And you know that, and it's measured in seconds. And the rate at which things cycle or oscillate is called angular frequency. It's 2 pi over that, right? But similarly, if you're looking in space, the amount of space or distance between from one crest to the next is in space. It's measured in meters. It's something different. It's called wavelength. It's the length of the wave, the length from one wave crest to the next, or in other words, the length of one cycle. Now that is called wavelength. You've heard of that in other classes. I don't know if we've talked about it much in this class yet, but it's called wavelength, and it's designated with the lowercase Greek letter lambda, and it's measured in meters, not in seconds. And by analogy, right, it drives the angular wave number, the space frequency, so to speak, right? So there's always, what we're always trying to say in the wave is anything that you think you understood in terms of time for an individual oscillator applies as well to space for the whole arrangement. So omega is angular frequency. It's cycles per time. It's 2 pi per the period. And k, the angular number, is 2 pi divided by the wavelength. It's a perfect analogy, a perfect counterparts. And I mean that k that's in the equation, right? So, okay, so therefore, remember, I'm just trying to understand. So omega is cycles per time. K is cycles per space. How many cycles you're fitting per each meter between the crests. So that constant that I'm trying to unpack is that, right? I'm just plugging in from what I just did on the other page. So omega over k is 2 pi over t divided by 2 pi over lambda. Well, the 2 pi's cancel. So apparently this constant omega over k, this constant omega over k means something. It's the distance from one crest to the next divided by the time elapsing from one crest to the next. So if you were standing at Coney Island or Far Rockaway, if you're standing at the beach and you're watching wave fronts come in and hit you in the face, lambda, the numerator of that fraction is so basically what I'm saying is, say lambda is like 6 meters and say period t is like 2 seconds. What that physically means is that you're standing there and one wave comes in and hits you, and then you wait 2 seconds and the next wave hits you, and the next wave is like 6 meters behind the first wave. So the next wave is 6 meters behind in space and 2 seconds behind in time from the first wave. So each of these, so what that means, so distance over time, meters over seconds, what this is speed, right? I mean, if I'm not, it's velocity, but I'm not worried about direction right now. Omega over k is v, but let's be careful now. I don't mean v as in dy dt. I don't mean the velocity of any individual oscillator as it's racing back to its equilibrium position. Those v's, those vertical v's, are changing all the time. They're accelerating, and their accelerations are changing all the time. That's the whole point of homework 1, right? When I say this v, I mean the length between wave crests. I don't mean the length along a y-axis, right? So this v is this v is the speed of propagation. This is the speed at which the wave pulses are flowing through the medium. In other words, this is along the x-axis. Textbooks and websites I call this the speed of propagation, the propagation speed, but textbooks and websites and stuff will call this phase velocity. That term might have been in your lab 3 too, I can't remember, but this is the actual, this is the speed of flow. So this is pretty exciting because this means, first of all, the wave equation is saying something even more specific than it looked like. It's saying right. So now the wave equation is packing in a lot of information into one small package. It's saying a wave is a situation where a wave is a disturbance in a medium, a recognizable disturbance in a medium for which any individual piece of the medium accelerates back home, back to the equilibrium axis at a rate that's directly proportional to its disturbance from equilibrium axis, and the constant of that proportionality squared is the rate at which this whole disturbance flows through the medium. I mean, that's a lot of information being packed into that one equation, but even more to the point, I know we've 4 minutes. the big exciting implication of this is that v squared, the flow rate, the propagation speed, the phase velocity of this wave is equal to omega squared over k squared. But remember, and omega and k refer to all the oscillators making up this wave. But remember, for every oscillator, omega was never a function of amplitude, right? Omega for an oscillator, like, for example, masses on springs, omega equaled square root of k over m, right? What was my point? My point is that for SHO, for simple harmonic oscillation, frequency is independent of amplitude. Frequency is determined entirely by parameters, which means in English, as long as you know, say these are all masses on springs, as long as you know the stiffness of each spring and you know the mass of each mass, then in advance, you know the rate at which they're going to oscillate, regardless of how you set them up or how far apart you stretch them at first or what you do with them, right? Each oscillator oscillates at a cycling rate that's fully fixed by what it's made of, right? That's what this means. That's the essence of simple harmonic oscillation, that it cycles at a rate in time that is totally independent of how you try to arrange it in space. Therefore, so if all of these oscillators are doing that, and if the speed of this wave pulse is fully determined by the oscillation rate of all of these oscillators, then the speed of the wave pulse is fully determined by what all the oscillators are made of. In other words, every wave propagates at a speed that is entirely fixed, constant, by and to its medium. This is our punchline of today. And there's 1 minute. What I'm saying, and this is a big deal, though. Big deal. What I'm saying is, have you ever noticed people talk about things like the speed of sound? They'll say the speed of sound as though there is one, right? No one says like the speed of cars or the speed of baseballs. I mean, a baseball can go a certain speed, but it can go lots of different speeds, right? There's not one speed associated with baseballs or cars or planets or electrons or anything. But with waves, the minute you specify the medium that the wave is traveling through, you've specified the ingredients for all the oscillations that create the flow. So the minute you say like air at standard temperature and pressure, then waves will ripple through the air at one and only one speed. And that speed will remain constant relative to the air. So the wave equation, which contains a V in it, the wave equation tells us the speed of a wave, and we can rely on that speed to be one number that doesn't change as long as we know what the medium is that it's traveling through. That's a big deal. That's why we love waves. They have speeds that are fixed to the medium. Okay, so we'll keep talking about like the exam and all that stuff next Monday, but it's definitely postponed. It's definitely postponed. I hope and I'll put it in the Google Classroom and have a really nice afternoon. Thank you for your patience. Yes, have a good one, people. Yes, thank you. Thank you. All right, now I'll turn off the record. Thank you, guys. Yes, have a good day. Awesome. Have a good day. Thank you. Turning off the hello, Michelle. I'm turning off the have a good day. Yes, have a good day. Have a good day. You good, Yavi? Have a good day.